Hello everyone, and welcome back to the episode 2.2, where we'll be implementing simple and multivariable linear regression in TensorFlow. In simple linear regression, I mean we'll be trying to, given a data set on the left, we'll try to predict a linear regression model, uh, a straight line here as shown in the right diagram. And for multivariable linear regression, given multi-dimensional data as such here, we'll try to predict a model, which in this case will be a hyperplane. So basically in this video, we are going to implement simple linear regression in TensorFlow, multivariable or multiple linear regression in TensorFlow, and then the same multivariable linear regression with some other, matrix format. This will be this type of, what to say, implementation will be useful in case of neural networks where there will be more number of weights. And then obviously we'll use tensorboard to visualize our defined model graph, then also to see the loss or the improvement of our model after training. And then we'll also visualize the histogram of the parameters, and then we'll also see how we can save and load the trained TensorFlow model and use it to predict it, the later values. But before that, let's have a recap of the previous episode. So in the previous episode, we discussed the theory of linear regression, where linear regression is a supervised learning technique which predicts some real number like 10, 13, like predicting the consumption of water ounces or predicting sales or predicting house prices. And basically linear regression model tries to learn a model from the data so as to best fit the given output data. And once the we get the linear regression model, the best fit model between this, then we can use that to predict uh, the output for new input which is not even in the training set. And if there are like single variable or single independent input as such here on the left, then we call it simple linear regression. And if we have multi-dimensional input like here TV, radio, newspaper, so then we call them as multiple linear regression. And if you haven't watched the previous video, I encourage you to go and have a look at that. And then we discussed about the how this linear regression model can be trained with gradient descent. Given this input data, we define this model, which is simple linear regression model is equivalent to a straight line. W and B are the parameters. We initially start with random value of W and B. We predict some value, we compare it with the original value, we compute some error, and based on that, over all the training set, we compute a loss or a cost function. And that cost function is then used to learn the best fit of parameter or best value of the parameters W and B using gradient descent by going step by step downhill till we get the best value of W and B. And either it's positive gradient or negative gradient for the cost function, we can use the same formula to update the weight or the bias values. And learning rate is an important parameter, you have to choose it wisely. If you have very high learning rate, it will overshoot, it will not converge. And if a very small learning rate, then it may get trapped in local minima. It will take a long time to converge. Then we discussed like there will be like a batch gradient descent, stochastic gradient descent, and mini batch gradient descent, where based on how many number of data we are using to update uh, for the weight value, to update single or to do a single update, how many number of examples I use, these three are categorized. And you can have a look at the previous lecture for detailed explanation of this. So this graph shows in case of batch gradient descent, where we take all the examples for doing single update, it's quite smooth. And in case of stochastic gradient descent, where we take single example to do the updates, it will be jittering a lot. So this is the 2D space where we learn a line, and 3D space or multi-dimensional space where we learn a plane. So and that was simple linear regression. In case of multiple linear regression, is the same way, but instead of just one, we'll have three inputs. We'll have three weights, W1, W2, W3, and the model, instead of A equal to W into X plus B, will now be A equal to W1 into X1, W2 into X2, plus W3 into X3 plus B. And the same way we'll compute the cost function, and similarly we can use the gradient descent to update each of the parameters. Okay, and so I guess that's all from the recap, and let's get started with this episode. And in this, we'll be implementing these two examples. So first we'll be given the population. We have to predict the profit of a food truck, and we'll not do this example. Instead, we'll do this example. Given the size and number of bedrooms, we have to predict the price of a house. So now the output model here will be W1 into X1 plus W2 into X2 plus B, because there are only two features. Okay, so for simple linear regression, let's do this. Given this data set, we have to somehow learn this kind of model. So let's me go to my Python notebook. And so I have opened this notebook in this directory where my data is and my code is. So you can put all this, I'll provide this in the GitHub, so you can put all this in one folder, and from there you can launch your notebook. So this is a linear regression. Let me clear all the outputs first. So okay, so kernel is ready, and let's get started. So our problem is to predict the profits for a food truck in a city. So first import the necessary libraries, and excuse me, so let's import this data. So it has two values, population and profit, and these are some of the examples. These are the populations and these are the profits. And let's do a data.describe, which gives a overview of how many number of populations are there. There are 97 samples, mean, STD, minimum, and how many of it computes 25% and all that. You can have a look. And this is not the best model to get the best output for this data, but this I just wanted to show you how you can do the linear regression problem. So this is just an example, example code. So let's see how many datas are there. So obviously it's 97 samples are there, and data X and data Y will be population, will be the input data X, and profit will be the output data Y. Let's do a scatter plot for this. The scatter plot will look something like this, and if you want to do a simple plot, plt.plot, so you will not see this gap. It will look something like this. So it's scattered everywhere, and you can have a look at the shape of the input and output is 1 comma 1. And if you want to have a shape of, or you want to visualize the data samples, these are the data samples and these are the output. So our simple linear regression model is A equal to W into X plus B. So let's get started with the TensorFlow thing. So first we'll define the inputs. So inputs in the sense X is our input and Y is our true output. So this is a supervised learning. We know the Y, and we have to predict, we have to learn a model A which will give output similar to Y. Okay. So let's run this. We'll define placeholders. So placeholders are kind of variables where we'll feed the data later, and then we'll define the parameters W and B here, and we'll initialize them with 0. But now till now, like I haven't, I'm just creating the graph, and then we'll define the linear regression model, which will be Y predicted X into W plus B, and then we'll define the loss function as we saw on the slide. So loss will be y minus y predicted square root and taking the mean of that. So if you see here the formula, uh, or here somewhere, so cost is summation over all the data samples, and a is predicted minus true and whole square. So this is the loss function, and let me run this. Okay, and then so this is then we'll define the learning algorithm. The gradient descent optimizer will give a learning rate 0.001. We're taking a small learning rate, and then our training operation will be that this optimizer should minimize this defined loss. So we'll give optimizer dot minimize this loss. Okay. So next, in order to visualize the weights, the bias, and the predicted output plus, cost, will create summary files. So as we discussed in the episode, TensorFlow episode, I think episode 1.2, that in TensorBoard, we can, plot the graphs and all this loss, histogram, etc. from the summary files. We'll create the summary files where we'll write this during the training. So we'll define these three values, we'll define the cost, and then we'll use a summary merge a tf.summary operation to merge all the summaries in one variable, merge summaries. Okay, and then as I told, we can also save the TensorFlow. Let's run this. We can also save the TensorFlow model, and for that we'll use a saver object, and we'll create a variable saver equal to tf.train.saver. So this will save the trained model, which we can use it later whenever we want. Okay, so let's run this also. And now till now we just define the graph, and none of the tensors or value will pass in the graph unless we launch it through a session. So now let's launch it through a session. And yeah, this is another variable which I created in order to plot the loss here in this notebook, and whatever summary we define, we can plot the loss through tensorboard. Okay, so it's very simple. So we'll start a session, then we'll create a writer file, tf.summary.file writer, where it will write all the summaries. And you can see in my tutorials here, there is no folder named simple linear regression. And here we are going to create a folder named simple linear regression summary, where the graph will be there. And then we'll run an initializer where we initialize all the variables. And then we are going to loop over 300 iterations. So you can give as many iterations, and depending on the data and the model. I'm just giving 300 here. And here I am doing gradient descent over each example. It's kind of stochastic gradient descent. So because for each iteration I am looping over each example, and for each example I am running these two operations, this training operation, which is minimizing the loss, and then I'm also computing the loss here, and then I am you know running this summary merge summary operation. And we can feed the data using placeholders. So at the beginning we created placeholders x and y, and in this x and y we are feeding this data x and y. Okay, and then since I created this variable cost history, I'm appending all the losses here so that I can plot it later and have a look. And I'm doing this not for every data but for every iterations. Okay, and then I'm also going to plot loss here so that we can see that we are learning something, or our loss is reducing for each 20 iterations. Okay, and also we are going to write those laws in our summary file, so that we can visualize it in tensorboard. Okay, and then final value of w and b, I'm getting it after all the iterations here, after all the for loops have run, by running this w and b operation. And then I'm saving this model using the saver variable we defined above, saver.save this session in a folder called saved model, and our model name will be model final. Let's give a linear regression. Okay, and then I'm finally closing the summary writer. Okay, so let's run this and let's see. So okay, so there is an error here. It says training op is not okay. I forgot to run this, sorry. Okay, let's run this now. So you can see the loss was 5.84096, but as we are training or iterating, or we are updating weights using gradient descent, the loss is reducing. So this just shows that our algorithm is doing well. And using this cost history variable, we can plot and see our cost. So you see, so it's just reducing. So it means our algorithm is kind of doing well. And then we can also take 5 examples, for example data x0 to 5, and we can predict it with our value that we have learned, w value final and b value, and we can test it. Okay, let's see. So what was w value again? Yeah, w value is our final trained best value of w and b. So on that, now you see this is the predicted value, and these are the 5 test values. You can see they're not very great, but okay, for demonstration this is okay. And any new value you can predict using this formula. You have to give new value of x, and we know the w value and b value, and we can get new value of y. So, and let's print w value and b value. Okay, now in order to plot the graph, I will do a test prediction on entire training data set. So x test is equal to np.array of entire data x, and y is obviously this. and we'll compute the y predicted for entire training data set, and let's do a plot and see. Okay, so you can see this was our data set, this purple or blue color points, and this line, straight line, is our regression model A equal to wx plus b. And we can do a scatter. This is the normal plot. If you want to do a scatter plot, you can do the same way. It's just for showing, like, no need of that. So you see our model is kind of got a good fit, but we can improve it further, by changing some parameters like learning rate, training it over more number of iterations, or training it over different batch sizes. Okay, and then our model will be saved in this here. Let's see, our model is saved in, yeah, saved model, and these four files. So the meta files will be the graph, and checkpoint will be the variables, I suppose. So these are the files where our TensorFlow model is saved, and if you want to load it, then model final, what was the name of the file? Let's see. It's lean okay, so lin_reg. So if you want to restore it, then we have to start a session. So you just first note this value of w value and b value, this 0.996 and minus 3.9213, and this is the saved model. And if you want to reload it in some other script, or later, maybe suppose you trained your model and you want to deploy it, so in that case what you'll do, so we'll first import this graph using tf.train.import meta graph, using this meta file, and then from this graph will then restore this uh, checkpoints in this session ses. Okay, then we can get our w value, final value, and once we get the w weight value and b value, then we can simply predict any value y, because it will be w into input x plus b. So let's run this and see and what it gives. So it gives, weight final as 0.996 and bias as 0 minus 3.921, which is what our model had learned here. Okay, so I hope you got an idea of how simple linear regression is implemented here. And let's have a look at the TensorBoard, and let's see what are the things we wrote in summary file. We can visualize it there. So to visualize our stored, summary files in TensorBoard, let's launch TensorBoard. So first I activated my TensorFlow environment where I had TensorFlow, and TensorBoard minus minus log directory, and you have to give the directory name. So my directory is this whole file. Let's see, and then minus minus port 6006. And in order to run it, you have to give local host 6006 TensorBoard. So let's see whether so it's still not running. Have I? So okay, so my TensorBoard is not running yet. Okay, so now it's running. Let's refresh this. Okay, I know this error, so let's quit it first. It's because I'm in C and I'm giving through path through D. Let me first enter D and then give the same thing. Let's see, now it should take. Okay, and let's refresh it. Okay, so you see there are four summaries that we wrote: scalar for loss, the graph, distribution, and histograms. So this is the loss, and this is the smoothing, how much smooth you want. We don't want any smoothing, then it will be normal, what we saw in our Python notebook. So this was the graph, and it's something similar here. And then this is the graph means your model. So if you remember, we gave name scope. In name scope input, we defined input and output, and then in name scope parameter, we defined bias and weights, and then in name scope regression model, we defined this y predicted is equal to input wx plus b. And then the loss function, sorry, let's minimize it. So loss function was getting predicted value from here and true value from here. Then they are computing gradient, and which was finally fed to gradient descent, and then we were saving our model here. Okay, so you can it helps to visualize your models. And then distribution, let's see, this is the bias. So initially we started with 0, and the final value, if you remember, it was minus 3.9 something. And what was the final value of bias? It was minus 3.92, and weight it was 0.99. So that's what we can see, that iterating up to 300 epochs, it went to minus 3.9, and weight which was initialized to 0 went up to 0.99. And this is the y predicted value for this w and this bias, how this prediction value graph will move. Okay, and if you want to visualize the individual graphs, you can visualize it here. And then another feature of histogram, which gives a distribution of weights, so over different iterations. So this is the 0th iteration. This was the distribution of bias value. As we keep on training, finally, at the 280th or 300 iterations, our bias value was minus 3.9. So it is in the range of that minus 3.8 to minus 4. Similarly, weight, we started with some zero value with zero epoch, but as we keep on training, finally we got a value of 0.99 or 96, and this is the distribution, this is the weight distribution. And similarly for the predicted value of y, so you can visualize histogram through this. Okay, so this all from tensorboard, from for simple linear regression. Now let's go and implement multiple linear regression. Okay, so in multiple linear regression, as you can see here, okay, this is wrong, it should be some price value here. So if you see in multiple linear regression, in our case we are having two inputs, so we'll have two weight values, and our model A will be w1 into x1 plus w2 into x2 plus b. And for update, we'll be updating two w values, two weights and one bias, which in previous case was just one weight and one bias, because we had just one input. So let me first restart the kernel and clear all output. Okay, so here I am taking one extra mplot3d for plotting 3D curves here, because we have multi-dimensional data here, so we need a multi-dimensional space to plot it. So let's first import it. Let's see what TensorFlow version I'm using. I'm using 1.4, and so here you can see the input is size and bedroom and the output is price. So let's load this data, and the data which I use for this multiple linear regression and simple linear regression are from Andrew NG Coursera's course, this data samples. Okay, so you can see this data and you can have a data.describe, and so let's plot this and see. So you see, this is the size, this is the bedroom, and this is the price, and this is the data distribution of this example. So now you see, we have to do some feature normalization. It's because you see this first feature, it's in 1000, the second feature is in just unit 334, and the price is some lakh. So we need to do normalization so that it kind of comes in one standard range, and so that our model does not give bias to any of the feature. Okay, and we can do this by subtracting the mean value and dividing it by standard deviation. And now if you see your data, you see it has come in some specific range, the size, the bedroom, and the price. Okay, so in this way the learning will be better. Now let's plot, it will be kind of similar what we plotted before. Oh, this is a shape, sorry. So you can see the input shape is a number of samples by number of features or number of input data for each example. So we have two two inputs, size and bedroom, so we'll be having and 47 samples, so 47 comma 2, and output we have just one for each input, so it's just 47. And if you plot it, so it's the same thing. And so now our model, as I discussed, it will be w1 into x1 plus w2 into x2 plus b. And now our placeholders will have three values, x1 x2 for two inputs and y for the true output. And our parameters will be 3, w1, w2, and b. And our predicted output will be x1 into w1 plus x2 into w2 plus b, which is the multiple linear regression model. And we'll define the loss function, which will be same mean square error function, which you can do with this operation of TensorFlow. And then we'll define our optimizer, which again is gradient descent, and we're using a learning rate of 0.001. And so now let's create the summary, w1 histogram summary, w2 and bias, and then a scalar summary for cost. And then we merge all the summaries in a merge summaries variable using tf.summary.merge all operation. And this is launching of the session for multiple linear regression. Like similar, we are using a cost history variable just to plot the loss here. Then we are writing this in a different directory, multiple linear regression summary directory. We are initializing all the variables, and I'm looping over 1000. I don't know why did that. Let's do it for same 300. Let's see what happens. And I am looping over all this data. So x1 x2 y, and I am feeding it through placeholders x1 x2 y through a dictionary feed, and then I'm storing the cost in this variable for each iteration, and then I am for each 20th iteration I am writing it to summary file and I'm printing the loss. And then finally, after all the 300 iteration, I'm getting the final value of w1 w2b, and then I'm saving this model into saved model. Let's give multilinear regression model and model final multi. Okay, so have I run the summary? Yes, so let's run this. Let's see what we get. So you can see the loss from 0.52 to wow. Okay, name saver. Okay, I didn't define the saver operation. Okay, I'm sorry. Where was the saver operation? Okay, so I forgot to do this. So let me define it somewhere here and run it and run this again. So you can see the loss is reducing, and let's plot our loss curve, and you can see how nicely it has reduced to very small value till we get the best value of w and b, where our loss will be the minimum. Okay, somewhere here actually. So once our model is trained, that means we got the best value of w1, w2 and b, then we can predict any value for any new data, which is any sample which is not even in the training set. So using this formula of x1 into w1 plus x2 into w2 plus b. So let's consider first 5 samples of our training data, and let's see. So yeah, so you see this is the predicted value and this is the true value. So yeah, you can see not very bad. So actually, if you remember, we normalize the data, that's why we are getting like this. But if you want to get the real price, then you have to again what do you say, we subtracted it mean and divided it by std, or I mean standard deviation. So you have to kind of add this. So you again add the mean value and you multiply with this as standard deviation. So you get something price in this range of, what do you say, yeah, some lakhs, 39 lakhs or something, or 3 lakhs 99,000, rather than getting some float values like this. Okay, so you have to do that reverse. Now just to plot it, let's do a prediction of our model on all the entire 47 samples, and let's see what our model is predicting. So let's plot this, and for plotting this I have defined two surface x1 x2, because I have to plot a 3D curve here, and it will give this plot. So this was our data set, and this is the hyperplane. So given any new data, suppose between 0.0 and 1, we'll map it here, we'll map it here, and then we'll predict the price here in the third dimension by using this formula. Okay, so this is how you can do a multiple linear regression. And similar to the simple linear regression, even the saved model in multiple linear regression can easily be loaded and used anywhere. So you have to just load the meta graph, the meta file, where you have saved it by giving the correct path, and then you have to load the checkpoint, and then you can get the final value of w1 w2b, the best value of w1 w2b, and using that you can, in this linear regression model, you can predict any value for any input x. Okay, and if you run this, we get three values: final, w2 final, and bias final. And if you compare it, 0.88 minus 0.05 minus 0.0015, it is similar to what our final value of the model which was predicted. Okay, and similarly we can visualize this summaries in tensorboard by the same way we use for simple linear regression. So we enter the D directory, we type tensorboard minus log directory, and we give the correct path. So you have to remember to give the correct path here. So now the summaries were saved in this folder, multiple linear regression. So just copy this and just paste it here, tensorboard minus log directory, and then minus port 6006, and then you have to type localhost and you will get this. So this is the loss, and if you don't do any this, so you can see this is the loss function, same as we saw in notebook. And if you want to smoothen it, you can smoothen it. Then this is the graph, or our model. And then this is the distribution of bias. It's starting from here and going somewhere here. Over iterations, it's reducing to the small value minus 0.00, as you saw. And then weight 1 is going to 0.008 something, and weight 2 was also in some minus 0.00 something. And similarly you can just have a look at all this. And then histograms, you can see the bias histogram as we move over different iterations, the weight histograms, and the weight 1 histogram, the weight 2 histogram, etc. And one important thing that I wanted to discuss here is when we are feeding this data to the model through feeddict, here we are feeding it example by example. So one by one, we are looping over each example and then feeding it. So another way is, instead of giving just one example, giving the data one by one example, we can give it in batch size, like a batch of 100 or batch of 200 something. So we'll see this batch wise in later when we do neural network. And another is, you can give the entire training data set at once. Okay, so suppose this was, I'll close this loop, and instead of updating the weights after every it was kind of stochastic gradient descent, and let's do a normal, a normal gradient descent over all the training examples. So let me give you the entire training data set at once, and let's see x2 and data y. Okay, so let me run this and let me see what it gives. So you see now the error is from 0.97 to 0.45. Iterate it over more, then maybe I'll get something more. And now the weight values and b values also change. So this is also a hyperparameter, what batch size to choose and all. So when we train tougher, or or deeper models, then this will come in picture, choosing batch size depending on memory, and this also play a role. So even the plot will change now from this to this. And if you train it further, it will further reduce. I just wanted to show you. And even our this multi-regression model also changed. Okay, so that's all from this. And but yeah, there is one more thing that I wanted to discuss, and that is doing the same multiple regression through some different way. Okay, so let's discuss that. So this was our example. We are having size of the room, we are having the number of bedrooms, and the output was the price. So for these two features, what our predicted model, or the multiple linear regression model, was w1 into x1 plus w2 into x2 plus b. Consider, suppose there are n features, so instead of x1 x2 there may be as many features. So for in that case, the model will be w1 x1 plus w2 x2 and so on up to wn xn plus 1 bias. Okay, so here x1 x2 x3 up to xn, they will be the placeholders for each of the feature up to 1 to n. Okay, as we declared in our code in the notebook we just saw. And w1 up to wn will be the weights for each of the features. So each features are being weighted by one parameter w, and overall we add a bias term. Okay, so this instead of like the way for two features, what we did was we defined y predicted as w1 into x1 plus w2 into x2 and so on. Instead of this, if we use matrices, we can simplify all these operations. So let's see how we can do that. Okay, so uh, okay, so let's see here. So the data points, just consider the first sample. Okay, so and instead of x1 x2, consider up to xn. So the data points can be written as 1 into n columns. Okay, one row into n columns, and the weights, which is w1 up to wn, they can be written as n rows into one column. So when you multiply, x1 will multiply with w1, x2 will multiply with w2, x3 will multiply with w3, and xn will multiply with wn, and they will all be added up as in a matrix operation. Okay, and we can do this using placeholder, defining placeholder such as x is equal to tf dot placeholder of shape 1 is to n, and for weight it will be tf dot variable tf dot zeros n comma 1 n comma 1. So here we are initializing the variables with 0. Okay, so this is just for one example, and actually this one is this example I taken from this blog. The link is here, and I'll provide the link. You can go and have a look at this blog. This is really nice blog. So if you take again this was the data. Now this will be the answer as I told you. So this into this will be x1 into w1 plus x2 into w2 plus x3 into w3 plus xn into wn, and on this we'll add a overall bias of plus b. Okay, now now you consider instead of one examples there are m examples. So in that case we'll be having m rows into n columns, so each row represent one example. Okay, so this is the first example, x1 of 1, x1 of 2, x1 of n. Then this is the second example, suppose 1600 300 here. Then third example 2400, and the last up to this end. Okay, but the number of weights remain same, w1 up to wn. Here the shape will be m rows into n columns and n rows into one column, and we can easily do matrix multiplication of this, and we'll be getting this row will multiply and add up with this one. This second example will do this one, and so we'll get m rows into one column, so each row will represent one output. Okay, and we'll get here just one output, this one. Okay, and this is without adding the bias. So you can define it here like this: x is equal to tf dot placeholder tf dot float m comma n. M is the number of samples, and each sample is having n features, and the weights will be tf dot zeros n comma 1, and y will be a matrix multiplication between this x and w. Okay, finally each of this x weighted sum will be added to one bias, so this bias will add to all these rows. Okay, so it will add to all these rows, and for each so we finally will get m rows into one column value, and each row will represent one output or one predicted values. Okay, so yeah, so let's have a look at this in the notebook. Let's see how we can do this. So I have this notebook here, so let me restart and clear the output, and it's for matrices based multiple linear regression. So it's the same problem we did, but the way we define the placeholders and the variables will be in a matrix format. So let's do it. So I'm going to import a TensorFlow, and I'm going to run my data. I'm going to plot it, and I'm going to normalize it. So yeah, one thing here is the number of samples we have is 47, and each sample has two features. So there are two inputs, size and bedrooms. So the number of inputs for each sample is the features. Okay, so number of features we are having is 2, and yeah, what is this? Oh, this is the same plot. Okay, so yeah, forget about this one now. Yeah, so for two features, the model will be like this, or in matrix form is simply w into x plus b. So now we have to create the inputs, placeholder for placing the inputs. So if you remember in the before example, the way we created placeholder for inputs was we're defining x1, x2, and y. But here we'll not do that. Here instead of x1, x2, we'll just give 2 because we have two features, and we'll give just one name x, and this will give the shape of x. So if we are using all samples at once, so the shape of the placeholder will be total number of samples by 2, as we saw in the slide, m comma number of features. Okay, so this we can write also as number of features instead of 2. If there are more than one feature, so it will just take that. In this example there are only two features, and y it will be number of samples comma 1. So for each sample we will have one out. Okay, Now this is one way when we know that how many samples we want to give. Suppose you don't know how many samples you want to give during the training. So like you maybe you want to give a batch size of 2, a batch size of 10 or 100 or simply 1. Then in that case you can define this placeholder with a shape of none comma 2. Okay, so this is the shape and y will be none comma 1. So in this none you can give any number of inputs, but here I'm just since I have less number of samples, I'm just giving the total samples. Okay, and let's run this. And then weights also, instead of defining w1 w2, we can simply define weights as tf.0 number of features comma 1. So it will be a column matrix of number of features comma 1, as we saw it here. Yeah, so it will be n rows into one column, and is the number of features. So for each features we'll have one weight. Okay, and we'll have overall one bias. So you did this, and then we'll define the regression model as a matrix multiplication between data x and the weight w, and then we'll add overall bias. Okay, and then we'll simply define the loss function we have been defining. So I just wanted to show you this. So tf.reduce mean, this means it will take a if you remember the formula of cost function, we compute the cost and we average it over all the samples. So this one does this, but instead of you know doing this many places, you will find 1 by 2 into number of samples. So this is just taking the square and this is dividing by 2 into number of samples. Okay, so this is just the scaling by 1 by 2. So either you can use this. Here there is no divide by 2 term, here there is divide by 2. Okay, so yeah, and then we'll define the optimizer, gradient descent optimizer with learning rate 0.01. And similar like before, we'll create summary operations, and then we'll create a saver to save the model. And then data which we are going to feed in, we have to reshape in the format we have defined the placeholders. So in this case, we define in the shape of number of samples by number of features too. So if it was not you are planning to feed as a batch of 10, then you have to somehow, the data which will go in this feed dictionary should be in form of 10 comma 2. And if we are just going to feed like one by one as we were doing looping over all the examples, then it has to be in the shape of 1 comma 2, and this has to be in the shape of 1 comma 1. But in this case I'm going to feed it all together. So this, I'm just doing this for I in range of 1000 iterations, and I'm just feeding the entire data set, and whose shape is number of samples comma 2, and this number of samples comma 1. Okay, and then final value of w and b, I'm getting it after running it all over iteration, and then I'm saving the model in this folder, in this file name. Okay, so let me run this and see what I get. So you see the loss, it's from 0.48 and it's reducing up to 0.18, and it will reduce further if you train it for further iterations, or if you take batch sizes. And also I didn't show how to create different batch sizes and feed it, because there are very less number of samples. Maybe in future logistic regression or neural net, I'll show you how to create batches and feed into it. Okay, so if you plot it, you will see your loss function reducing. And then yeah, then this one here, this, suppose you want to predict, once you have trained, you've got the final value of your w, and you can, based on that, you can do a matrix multiplication between your new test data and yeah, just new test data and the learned w and b value, and you can get anything. Here I'm just taking 5 samples of the training data, and in this case, if you simply run this and try to print the value of w, you won't get it, because you have to run this through a session. Okay, so let me run this and show you. So in the first case, this predicted value, it will just say tensor shape of 5 comma 1. So there are 5 samples, for each samples we have one output, but it will not print it out, where the true value is this one which is printed. So in order to get this value, you have to run a evaluate one. So we will create a session dot run this one, and then eval. So when you do this, you will get all these predicted 5 values. These are the predicted 5 values, and these are the actual 5 values. Okay, so in order to plot, I will run this uh, I'll run the entire data set through this learned predicted model to generate, predicted values for all this data, all the 47 samples, and I will use this to, this is the final value of weight and bias. So weight will be, two-dimensional, one for each feature, W1, W2, and I'll use this to plot, and you can see the plot as you saw in uh, the previous here multiple linear regression when we train it over entire data set rather than looping over the single examples. It was something similar. Okay, so this is our final model, and similarly you can run your saved model from the checkpoints, and you can get the values of weight 0.48, 0.16, and this which was our learned model. Okay, and similar to the examples I've shown, you can also see your, what to say, tensorboard, and for this example, and but you have to give the correct path. This one I didn't copy it, so it's pretty simple. You have to just go to your place, and this is my new directory for saving the multiple linear regression summary for matrix based approach, and minus minus 46006, and let's enter it. And it's specified when db is not specified, what error I got. Okay, summary, let's run it once again. I don't know what the problem is. Okay, so okay, I'm missing, it should be minus minus log directory, sorry for that. It has to be one more minus. And okay, so now let's go and have a look at our tensorboard. Local host 6006, and you see the loss, you see the graph, you see the distribution. Now this is the bias which is really fluctuating, and now the weights, there are two weights value, so it's kind of in this range. And similarly the y predicted will be due to these two weight values. The weight is two-dimensional, actually it's not just one value, it's a two-dimensional weight. And w, it's w, what is y is w into x plus b, so it will be something like that. And for histogram also, so these are the distribution of bias for 1000 iterations from 0 to 1000. And this is the distribution of weight. Weight is it's a two-dimensional weight value. So if you remember, if you see here, our weight value was, what do you say, finally 0.48 and 0.16. So somehow you can see this is around 0.16 and this is around 0.48. So it's two weights value, and they're over training, they're taking this path. And similarly y value will have two peaks corresponding to w1, w2. Yeah, just to visualize how is the distribution of your parameters. So pretty much that's all from this episode. And yeah, I took this matrix with multiplication, few of the figures from here. You can read this blog, it's really nice blog, and he has also given code for implementing this, and he has also explained some batch wise training. And also I did it in from all layman's term, so as to make so as to explain everything from scratch. But you can have a look at this also to in order to implement it. Here he have explained how to do the batch wise and all. However, I will be covering the batch wise thing in the later episodes. So yeah, I'll provide the link for this blog. And pretty much that's all from this episode. And in the next episode we'll do the same implementation of simple and multi-variable linear regression, but we'll do that in keras, and you'll see how easy it is compared to TensorFlow. And I personally like keras, no offense TensorFlow users, but TensorFlow is pretty famous, but I like Keras. So that's all, and tune into the next episode for that. And if you like the video, you can hit the like button, you can comment your queries, you can subscribe, and if you want to support me, you can support me on Patreon and PayPal. The links will be given below. Until then, keep learning and keep exploring neurons. Bye.